Am I audible to all of you?
Yes, sir.
Okay, good morning. Let's start with today's class. Before we commence today's class, let's have a relook into the things that we have covered in the last class. Last class, if you can remember, we have covered classification of output stages or classification of power amplifiers, as you can see here. And we discussed different types of power amplifiers, namely class A, class B, class C, and class AB. And we have even mentioned last class the criteria for classification of these amplifiers. The first criteria would be the operating point and the output current flow, whether output current flows for the entire 360-degree for the input cycle, or it only flows for the part of the the input cycle, the output current flowing for only for the part of the input cycle. That's how we have classified different class of amplifiers. Class A, if you look at the current flows for the full input cycle, the output current flows for the full input cycle. In such a way, we are choosing Q point and the input signal. Okay, input signal is usually the sine wave, as you are seeing here, which is 360-degree. And for the class A type of amplifier, the current output current flows for the entire input cycle. So that is the definition of class A amplifier. Operating point is exactly chosen at the midpoint of the load line. We have expanded this through the output characteristics of a transistor, which is a graph of VC versus IC. And this we have drawn the load line, a DC load line. Okay, and we can choose operating point anywhere in the load line. That decides the class of amplifier. If operating point is chosen at the midpoint of the load line, so we can produce a full output cycle, as you see here. Okay, the collector current flows for the entire 360-degree for the full input cycle. So these kind of amplifiers are called as class A amplifier. Okay, but the phase shift also I told you here in class A. So there is a phase shift between uh, input waveform and the output voltage. For instance, you can see here for the base current waveform and collector emitter voltage waveform, they are out of phase. 180-degree phase shift exists here. Even with reference to the collector current and collector emitter voltage, there is a 180-degree phase shift. As you can see, the positive cycle here, and here we have a negative cycle in the collector emitter voltage. So that is those things students are supposed to observe here. And we have discussed even different waveforms, namely base current, collector current, and collector emitter voltage waveform for class A operation. And then we have told about efficiency, which is 25 to 50% efficiency. In today's class, we'll prove why the efficiency drops to less. Okay, so we'll see that in today's class. Second type of amplifier is class B amplifier. Here operating point and input signal are chosen such that the output signal is obtained only for one half cycle of the input cycle, one half of the input cycle. And here the Q point is exactly on the x-axis. And again, the current flows only for 180-degree, that is a half cycle of the input signal. We have shown even waveforms also. As you can see, the only the negative cycle in case of VC is produced. In case of collector current, the positive cycle is produced. And for the full input cycle, we are applying input cycle a complete 360-degree, but at the output we see only the half cycles here, positive half cycle for collector current and negative half cycle for the collector emitter voltage. Reason for this is they are 180-degree out of phase. And as you are seeing, same thing in the waveform also. Okay. Okay, next is efficiency point. Efficiency is 78.5%, which is better than the class C amplifier. Class C amplifier. So here again the definition is the Q point and the input signal are selected such that the output signal is for less than the half cycle of input cycle we are exploring. So that is the definition. The Q point is shifted below the x-axis for this. Okay, and you don't see even half cycle in the output waveform. Okay, we see the a small a portion of the output cycle. Okay, so again here the conduction angle is less than 180-degree, as you can see here, less than half cycle you see at the output. This is the voltage waveform, and here we have a current waveform. Okay, both the waveforms you see less than the half cycle here. Reason is the operating point is chosen below x-axis. Okay, and for the full input cycle that we have applied, only the part of the output cycles you can see at the output. Okay, so these are the waveforms of both input and output for class C operation. Conduction angle is less than 180 degree. Okay, uh, and efficiency is 100% for this. Okay, so that's very good from efficiency point of view. Next is class AB amplifier. Here Q point is and the input signal are selected such that output signal is obtained only for more than 180 degree but less than 360 degree. And we have shown that even input output waveforms and the output characteristics also we have shown with reference to this input and output waveforms we have shown here. And this efficiency lies between more than class A but less than class B. And this type of amplifier eliminates crossover distortion. Okay, so therefore it is used in audio systems, audio receivers and TV receivers. So these are the things that we have covered in the last class. So if there are any questions, I can take up. Okay, so to answer with reference to the last class topics that we have covered. In today's class, we are going to start with a topic called as Class A output stage. Okay, so just recall Class A amplifier. Just I will move to the definition of Class A. So this is Class A amplifier. We are going to discuss in more detail of Class A output stage. Okay, practical circuit, of course. Okay, so here we have discussed just the input output waveform, but we haven't discussed a practical circuit. But here it's a time to discuss a practical circuit that is suitable for Class A output stage. The best circuit or the most popular circuit that is widely used for Class A output stage is emitter follower. Okay, since emitter follower circuit we have not discussed in our course, so for your reference I have showed here below the emitter follower circuit, a BJT based emitter follower circuit. You can see here. Okay, this is an emitter follower circuit. So though this is not required for your syllabus point of view, okay, so we just use an application of emitter follower, okay, which is nothing but used in power amplifier, namely the Class A output stage. Why it is called as output stage? The reason why it is called output stage is because power amplifiers are used as a last stage in the chain of amplifiers. Okay, in the beginning we have proposed a power amplifier contains sequence of chain of small signal amplifiers like this. Okay, they are connected in cascade fashion here like this. So these are all a small signal amplifier, SSA, let us say. So this is also an SSA. Okay, after going through many stages here, the last stage has to be power amplifier. So this can drive the loudspeaker. Okay, so therefore this power amplifier, since it is a last stage or output stage of a chain of amplifier. So here we have a chain of amplifier. Okay, so the last stage is an output stage. Is output stage. So therefore the output stage also can be called as power amplifier. So here in our naming also this can be called as Class A power amplifier or Class A output stage. So I hope you understand why the name is output stage. It's because the last stage is power amplifier. Okay. Right. Okay. So here we are discussing the circuit that's widely used for Class A output stage. That's nothing but an emitter follower. The name itself tells you that emitter follower. The emitter, which is nothing but an output for this emitter follower circuit. Okay, so output follows the input here. That's why its name is called follower. Whatever we apply at the input, since we are taking output at the emitter, so therefore this circuit can be called as emitter follower. Alternatively, emitter follower is a common collector amplifier circuit. So we can call even vice versa also. The common collector amplifier circuit can also be called as emitter follower because its gain is usually 1, and whatever the output input that is applied, that the output follows here. Remember, this is a common collector, so output is taken at the emitter. Okay, for AC, this collector terminal becomes a ground. Okay, that's why it is called as a common collector. So therefore, so we can call common collector amplifier also as an emitter follower. So this circuit is used as an output stage, okay, or power amplifier, as in power amplifier, class A power amplifier. What is the reason of preferring emitter follower or common collector amplifier in the last stage of a chain of amplifier? The reason is it has got very low output resistance or impedance. So for this reason, the emitter follower is chosen as the last stage or class A output stage of power amplifier, because since the output resistance is very less, it can drive this loudspeaker. As I told you in the beginning, while explaining the features of an amplifier, the power amplifier output resistance has to be very less, and one such circuit that is preferred is emitter follower. So emitter follower circuit also has got very low output impedance, so therefore this can be used as a power amplifier, or this can be used as an output stage. So that's why I'm saying here this is most popular class A output stage. Okay, the students who are not aware of what is emitter follower circuit, which is shown here, this is like any other amplifier. This is also common collector amplifier. Only thing is, like common source amplifier we have seen in case of MOSFET. With reference to BJT, we have seen common emitter amplifier. This is similar to that. This is also another type of amplifier. Here we don't have any biasing circuits here. As you are seeing, this is biased using a constant current source. As you can see, this is a current source here. In this entire loop, from supply to positive supply to negative supply, the current flowing is nothing but I. Okay, so even though irrespective of the signal, input signal, whether you apply positive cycle here or negative cycle here, this transistor keep conducting or not conducting, but here in this branch, okay, especially the emitter to the negative supply, the current keeps flowing here irrespective of the positive or negative of cycle. That's why this circuit is called as a current source biasing emitter follower circuit. Okay, the rest of the circuit is almost same as previous circuit, except this one should pay attention to how we are biasing this emitter follower circuit. See, for any amplifier we need to set up a bias circuit. In other cases, we have seen that there was a voltage divider network, and in some case we have seen we have taken output and fed back to the input, that is collector to emitter, collector to base, bias network. And here we are seeing, we don't see such, but here we have just a current source here. What is the requirement of bias circuit? The bias circuit should provide constant current, collector current at the output. Even we use voltage divider network here or collector to base resistor here, the aim of all those bias network is to provide constant collector current, IC. Okay, we are trying with different networks, that's all. But here in this case, so here itself we have connected a constant current source, and that provides a current from source to supply always, irrespective of the input AC signal that we apply here. So transistor may or may not conduct, but still the current keep flowing from this emitter to the negative supply here. Okay, this kind of biasing circuits are called as constant current source bias, which are quite popular, of course, compared to voltage divider network or collector to base bias networks. Okay, let's come to the other part of the amplifier circuit. See, any amplifier circuit will have an AC signal, which is a small signal. Okay, so this is nothing but a model of a signal that is coming from antenna. Instead of providing direct signal coming from antenna, we are providing here a voltage source, and this signal will be very small, and this is usually the sinusoidal signal. Okay, because we assume that the practical signal also looks like a sinusoidal. Okay, so this is an AC source, AC signal that is coming, and the internal resistance of that is shown as R signal. This is signal resistance, and the input signal is coupled, capacitively coupled to the base of the transistor, and directly this signal goes to the base of the transistor where it gets amplified, and in this case it is just an the output here emitter, and the emitter follows whatever the input that is applied here. Whether you apply positive cycle or negative cycle, exact replica signal is produced here. During negative cycle, though transistor is off, this current keeps flowing in the load resistance. That's how the circuit works. Okay. But for positive cycle, the positive cycle remains same. But for negative cycle, the current source becomes inactive and it produces current at the output. And output signal is capacitively coupled to the load resistance. As you can see, there is a coupling capacitor here which is CC2, and there is an input coupling capacitor which is CC1. Okay, so these are the things which a student should pay an attention here. So output signal is measured across the load resistance which is RL. Okay, so this is an emitter follower circuit. Though the circuit is not required at this point of view, but since we are using this emitter follower circuit as a last stage or output stage in a chain of amplifier, and that particularly in class A output stage, this is the practical circuit that we are preferring. Okay, so here for your reference, I have given the expressions for input resistance and output resistance. That is a resistance measured between at the input point here with reference to ground, that is Rin, which is given by this expression. Students need not derive this expression, just you can remember this expression. And we are mainly interested in output resistance rather than input resistance, because in the beginning only we have mentioned that output resistance of this circuit is very low. This is a requirement for the power amplifier also, because this circuit has to drive the loudspeaker here, which we are connecting as a RL here, and therefore this circuit provides output resistance, low output resistance that is required for the power amplifier output stages. Okay. All right, this is the expression. So I advise you to remember this expression. This is Re, which is a emitter internal resistance or signal parallel with Rb divided by 1 plus beta or beta plus 1. So this is the expression for output resistance of emitter follower. All right, let's move back to the circuit now. Power amplifiers being the final stage of the power amplifier chain, therefore power amplifier are also called as output stage. The beginning only I mentioned that why it is called as output stage, because in the chain of amplifier, in the chain of power amplifier, the last stage of power amplifier, in the last stage we prefer power amplifier, that's why it is called as output stage. Okay, class A output stage. Now we are specific to class A output stage. Okay, here operating point is at the mid of the load line or center of the load line, and for all values of input signal, the transistor remains in the active region. Transistor doesn't move into the cutoff or saturation region since operating point is at the mid of the load line. Collector current flows for 360 degree of the input signal. So this is very important. Collector current is flowing for entire 360 degree of the input signal. This diagram depicts how the current flows. How the in this case we have taken the output signal, which is nothing but current signal flows for the full input signal here. So there is a sinusoidal input signal that we are applying for the entire 360 degree. The output current flows here. Okay, because the operating point is chosen at the mid of this load line here. So we know that operating point can be chosen anywhere on the load line. The reason why it is called class A is because it is chosen at the mid of the load line and output current flows for entire 360 degree of input signal. So that's the reason here in the class A we get conduction angle of 360 degree. All right, let's move to the other things, other details of this. Consider the common collector transistor configuration. This we have shown here, common collector transistor configurations. We'll go step by step. In the beginning, you may not see the complete circuit, emitter follower circuit, but only part of the emitter follower circuit we have shown here. You can see here we are taking output at the emitter. This itself shows that this is a common collector configuration, because we are taking output at the emitter. And for AC, this collector goes to ground. The collector is at 0. So let us consider common collector transistor configuration as we have seen here. We will see here for positive cycle how this circuit behaves. Since we are applying input signal as an AC signal, we need to verify this circuit for positive half cycle and even for negative half cycle. Okay, so let us try to verify this circuit how it behaves for both positive and negative half cycle. So here we are using one transistor which is connected in the common collector configuration, and there is a load resistance as you can see, and at the base and emitter there is a voltage VBE1. Since this transistor is Q1, named as Q1, so we are calling here base emitter voltage as VBE1, Why VB1 is important? Because we need to have here minimum base emitter voltage, which is 0.7 volts for the transistor to conduct. Okay, so this at any instant of time, if you want to make transistor turn on, we need to have here a voltage of 0.7 volts, which is nothing but cut-in voltage of a transistor. If voltage between base and emitter falls less than this, then transistor will be in off mode. It doesn't conduct at all. When transistor is in off mode, the connection between this point and this becomes an open circuit. So there is a power supply is get removed. Okay, so now we'll see how the circuit behaves at the emitter point here. Okay, so this is very important, base emitter voltage. So we need to maintain at any instant of time 0.7. Okay, any voltage less than more than this, obviously voltage Vi that is applied more than this, it transistor will be on. And any voltage less than this, input voltage less than 0.7 volts, transistor will be off, Q1 will be off. So these things, we must be aware of it. These are the fundamentals of a transistor. Okay, let's see, we have seen the common collector transistor configuration. Let's see for different cycles how this circuit behaves. For the positive cycle of AC input of sine wave that we are applying, output follows input, which is Q1 is on. As we have seen, for positive cycle, obviously the input rises and transistor will be on. Once transistor is on, what happens here? The output here, this behaves like a common collector. Output follows the input. The meaning of that is the complete positive cycle is produced at the output. So there is no problem with reference to positive half cycle. So entire positive half cycle is produced at the output. Reason is transistor is on. Okay, so since transistor is on, in this case we are maintaining at the mid of the load line. So complete positive half cycle is reproduced at the output. So there is no problem with reference to positive half cycle. Now let us see the voltage, output voltage and maximum output voltage which signal can go, and those things will just identify through mathematical expressions. Let's apply Kirchhoff voltage law for the collector emitter loop. This is the loop we are applying Kirchhoff voltage law, collector emitter loop, and see that. So we'll apply this here minus VCC plus VCE1, that is the voltage across Q1, plus V0, the voltage drop from here to here. You can see a signs here. Okay, we are starting from here, minus VCC plus VCE1 as you are seeing here, and plus V0. From here till ground we have voltage as V0. So plus V0 equal to 0. We can rearrange this and we can write expression for V0 as V0 is equal to VCC minus VCE1. Okay, so now let us see the maximum voltage V0 that exists here for the positive half cycle. The maximum value of output signal is obtained when Q1 reaches saturation. When Q1 goes to saturation, because Q1 can go all the way up to saturation and all the way towards negative cycle, it can go to cutoff. Now we are only verifying for the positive half cycle. Let's assume that when Q1 is in saturation, at that point we get maximum output voltage. So when Q1 is in saturation means VCE1 will be at saturation. So therefore this expression can be rewritten as V0 max, that is the maximum output voltage, is obtained when VCE is at saturation. Collector emitter voltage is at saturation. So therefore this expression can be rewritten as V0 max equals maximum output voltage equals VCC minus VCE1 saturation. I hope this is clear to you. This expression is very important for to plot the transfer characteristics of a class A output stage. Alright, let's see for negative half cycle what will happen to this circuit. Okay, so when negative cycle is fed in to this Q1 at the base and emitter, what is going to happen? As we said already, when we apply negative cycle here, when input falls less than 0.7, transistor will be turned off. When transistor turns off, you can see that output is going to be 0. So we have seen that output drops to 0. There is no output here exist for the negative half cycle. This looks like a positive off wave rectifier, right? We have seen positive half cycles are produced at the output. For the positive input cycle, this is an emitter follower, right? Common collector. But negative cycles are suppressed here. These cycles are not produced at the output here. So because output goes to 0, because transistor goes to cutoff, since input falls, input is negative. So this is a problem now. Now question is now how do we reconstruct even negative cycle? That's very important here. Okay, so let us see other techniques to reproduce this negative half cycles here. I hope you understood the problem, and slowly we will move on to how to reproduce this negative half cycle here. Now how to make transistor to conduct for both cycles. Positive cycle there are no issues, positive cycle transistor will conduct, but only for negative cycle the transistor was not conducting. Now for this what let us do here, let us do some changes to the circuit. Instead of having the load resistance here, we have connected here a current source. This is called as a constant current source, and I am not going to discuss circuit here for a constant current source. The circuit itself is a complex. We are not interested in designing a constant current source circuit here, but let us assume that this current source that we are employing here in this branch with the negative supply voltage provides a constant current between emitter to this minus VCC or emitter to ground. Okay, this current source produces or gives always constant current. That's why the name is constant current source. Wherever you connect here this current source in any branch, in that branch it provides constant current. Now the problem of negative cycle can be easily overcome by connecting a constant current source. So this entire bias is now can be called as biasing using constant current source. Even I told you in the beginning itself, whether you provide through the bias network or different bias network or provide a constant current source is one and same. The aim of even bias networks also is to provide a constant current at the output. So even here, instead of using here bias network, I am using here constant current source. So the requirement of the different bias network is fully met using this constant current source. So let us see now whether we are able to reproduce this negative cycle at the output just by introducing a constant current source here. For a positive cycle, no issues. We are able to get output because emitter follows the output here, so we are able to produce positive half cycle. But only problem is negative half cycle. Okay, let us see that how this circuit works for the negative half cycle. And here the change what we have made is we have provided a constant current source biasing as you are seeing here. Now let us apply Kirchhoff current law at this particular point here, at the emitter point here, and find out the expression for the current here. So IE1, that is the, let's assume that the emitter current for with reference to Q1, that is entering the node, and I is nothing but current due to the constant current source, this capital I, and IL is nothing but current flowing through the load resistor here. Now let us verify this for negative half cycle. So whenever we apply a negative half cycle at the input, transistor turns off. We know that Q1 is off here. In previous case we have seen that V0 was 0. Now let us see here whether V0 is 0 or it results in any other waveform. Let us see that. So since Q1 is off, now let us see that what is the role played by this current source here. So current source, what happens here, it flows through the load resistance now. Current is not 0. There exists some voltage here now, because even though here this Q1 is half turned off, so there exists here the loop here, right? Even this negative supply also we have connected supply like this. Don't treat this as something else. This is supply something like this. This is minus VCC. Okay, and here we have a ground. Look at here, there exists a loop here also, right? So now current flows through the load resistance here. The only current that flows through the load resistance is not because of this Q1, it's only because of the current source. So therefore the load current is now can be written as minus I. IL is now is equivalent to minus I, because IL and I are going to be opposite in direction. So IL will have the current which is equal to phase shifted I, which is nothing but minus I. Now what is the output voltage expression here? Output voltage is nothing but minus I times RL. The current that flows here is minus I times RL. So that means we have some output voltage exists even for the negative cycle that is applied as an input. Now let us find out here what is a minimum output voltage. We get it here whenever the transistor Q1 is in the off condition here. So let us see here, V0 minimum is nothing but minus I times R. That is the minimum voltage that we can get here. So maximum current then when it flows, that's the when this Q1 is in the cutoff, that is nothing but we can label this V0 as V0 minimum, and the expression is minus I times RL. Now based on this we can draw the transfer characteristics. So transfer characteristics is as shown here. So which is a graph of V naught versus Vi. As you can see, let us now write down the limits here for the transistor Q1 output voltage here. V naught max, we have already seen that. V naught max for positive off cycle is VCC minus VC1 sat. So whenever Q1 is in saturation, at that point output reaches maximum, that is a positive peak. But now let us see the minimum output voltage is minus I times RL. Whenever Q1 is off, under that condition V0 will reach V0 minimum. So we have seen positive limit or output voltage positive limit or negative limit also. So this can be shown as a transfer characteristics, as you can see here. So here we have negative minimum voltage here, and you can see the maximum positive voltage, it can be limited to VCC minus VC sat 1, VC1 sat here. So this is the maximum output voltage, positive output voltage. This is the minimum. The output negative can go up to this. That means at the output we can produce full cycle now. So this is what transfer characteristics is showing. Okay, and this is what the VB1. So curve doesn't pass through the origin. So there is a, it is slightly, it is shifted because of VB1. Okay, so VB1 is, but some voltage exists across even at the base emitter of the transistor. So this is a graph of V0 versus Vi. So it looks like this is a transfer curve for common collector configuration or emitter follower circuit. Okay, any questions so far? I hope everybody is following. Okay, next let us see some modification we are going to do for this circuit here. So we are thinking here, can we replace this current source with any other transistor based circuit, a practical circuit? We will see that. Okay, so because once we do optimization, the output should not change. As we are seeing here, there should be some positive voltage, there should be some negative voltage. In the very beginning we have seen that negative cycles are suppressed, but here we have shown here just by simple modification, that's by introducing constant current source or by biasing this Q1 transistor with constant current source, we're able to produce even negative half cycles also. Okay, so now we will see how to replace this current source with other transistor circuits. So one such circuit we have shown here, as you can see here. Whereas this upper part remains same, there is no change with reference to this part. This part remains same. The upper part is same, there is no change. But look at the lower part, instead of a constant current source, we have here transistor Q2, and you can see the base of this transistor is fed with a diode here and a resistor which is connected to ground. This is ground. Okay, and since it's connected to ground, zero voltage exists across this, and let us see here for negative cycle how it behaves. So you can see here this diode is connected to negative supply. The cathode of this is connected to negative supply, which is minus VCC. Large negative voltage exists at the cathode. Anode is at 0. So therefore this diode conducts. It is turned on. So it provides constant voltage to this base and emitter. Okay, which is cut-in voltage of this will appear across this. So this transistor Q2 will be on always. Okay, so the required current, whatever we expected earlier through the constant current source biasing, that is provided through this small circuit here. Always in electronics, see, the changes are very simple, but the changes will give you a maximum performance also. See, instead of having complex current source, we can have a simple circuit like which is made up of transistor Q2 and a diode Q3 with a resistor which is connected in this combination. Okay, so this substitutes the current source that is shown in the previous circuit. Okay, all right, let us analyze this circuit, how we can able to produce negative half cycle. We'll see that. Okay, so let us analyze the circuit here. So we are replacing current source by a practical circuit here, as you have seen here, and this uses transistor Q2, and collector current of Q2 is nothing but which is equal to I. That's nothing but earlier whatever we have shown current, same current now let us label it as I flowing through this. Okay, now let us see for positive and negative off cycles. When for positive off cycle which is Q1 is on, that we have seen earlier, V0 will be equal to Vi. Okay, And for negative off cycle, when Q1 is off, that is negative off cycles, let us apply KVL and find out what voltage exists at the output here. So once you apply KVL to this, let us see the expression for KVL. So we are applying from here plus and minus. Our loop is this, and there is, you can see all polarities we have shown. This supply, negative supply can be taken like this. This is minus VCC. Instead of this circuit, you can plug here. Now you can apply KVL within this loop, minus V0, that's you are seeing here. And when I move like this, we get collector emitter voltage across Q2, that is VCE2 plus VCE2, as you can see here. This is plus VCE2 and minus VCC. So this is minus VCC. Okay, so minus VCC. You can rearrange this and find out output voltage equation. V0 is equal to minus VCC plus VCE2. Okay, now let us find what is the minimum voltage when the voltage at the output reaches minimum. Because see, we are verifying negative off cycle, not the positive off cycle. For the positive off cycle, this V0 will be is exactly equal to Vi. That means the positive peak can easily reproduce at the output. So if I apply positive peak like this, so same cycle you see at the output. But the problem is with negative. Are we able to get this negative peak? That's the problem. That's the question. So let us see that to what extent this output can go minimum. So here you can see that the output can go minimum when this VCE2 is at saturation, when this is conducting maximum heavily. At that point only the output can go to a minimum. Okay, so minimum output voltage V0 minimum is nothing but same expression. So instead of V0 we have here V0 minimum. Under condition when we see collector emitter voltage goes to saturation, then we can see this V0 minimum, V0 as V0 minimum, which is equal to minus VCC plus VCE2 sat. So this is an expression which is required for the minimum output voltage. Okay, so we will see that here next how this can be used in order to plot the transfer characteristics. So now earlier we have shown the old transfer characteristics. Now we will show the new transfer. This is the old transfer characteristics. This doesn't have what we should say that this was based on the current source. Actually, this current source will replace with it will replace with this practical circuit now. So because of that, you can see that the positive limit, as we have shown already, which is VCC minus VC1 sat. Negative limit you can see here, minus VCC plus VC2 sat. So now you can see the new transfer curve. So this was based on current source. Now this new minimum output voltage expression is based on the practical circuit that we replace instead of current source. It's still better, you can see here we have still scope for more negative cycle here. So it is minus VCC plus VCE2 sat is the minimum output voltage, maximum output voltage. So between these two limits, okay, so the AC signal can flow in the output. So our aim is to produce full 360 degree at the output. The output current should flow for entire 360 degree. Okay. All right. So we have seen the positive limit and negative limit for the class A output stage, and we have seen even the complete circuit also. This is a complete class A output stage circuit. This circuit can be used in the as a last stage of power amplifier chain. All right, we have seen even transfer characteristics. It's a graph of V0 versus Vi, and we have shown that how we have expanded the positive limit and negative limit and the transfer characteristics. And a small change can be done, since if you compare this VCC supply voltage and the saturation voltage, and this can be neglected because this value is going to be very small when we compare with VCC. This can be neglected. Once we neglect this, you can see that what is the V0 max and what is V0 minimum. So it is plus VCC and minus VCC. That means at the output, the AC signal will oscillate between the two limits, which is plus VCC and minus VCC, as you can see here. Okay, so neglecting this VC saturation voltages here, the swing The positive swing can go all the way up to plus VCC. Negative swing is minus VCC. Between these two limits, output signal can oscillate. Okay. It can be minimum, but it can't go maximum beyond VCC. It cannot go minimum less than minus VCC. That's the meaning of swing. All right. So now let us see how do we plot this other waveforms. So waveforms are important here. So students should understand the way we plot the waveforms here. So this is nothing but VC1 waveform. So how do we show VC1 waveform? Look at VC1 expression here. What is VC1 expression? So I'll just show here. VC1 is nothing but VCC minus V0. How do we get this one? This expression we already showed in the beginning. You can observe here. VC1. Just rearrange this equation. So if you take this to the left hand side and V0 comes to the right hand side. So VC1 will be equal to VCC minus V0. Same equation we have written here. Okay. So VC1 is equal to VCC minus V0. So you know already the output waveform. It oscillates between plus VCC and minus VCC. Now can we draw the VC1 waveform? Any idea how to draw VC1 waveform? Because we already know waveform for this. VCC is fixed. And what is VC1 waveform? So if you take VC1 waveform along y-axis and time axis along x-axis, as you can see when the output was 0, when the output was 0, you can see VC1 will be equal to what? Just substitute V0 as 0 here. VC1 will be equal to VCC, right? So VC1 will be equal to VCC. Okay, so when V0 is equal to plus VCC, you can see here V0 is equal to plus VCC. VCC cancels and VC1 will be equal to 0. So now you can look at here, this cycle here. So VC1 here at this point is 0, but V0 is VCC. And again you can see that here V0 is 0. When V0 is 0, again VC1 will be equal to VCC. Okay, VCC. And again when V0 is minus VCC, here you can even look at from angle point of view also. This is 180 degree, this is 90 degree. Okay, so this is 270, this is 360. Let me write here angles here. So this is 270 and 0 degree. At 0 degree V0 is 0, VC1 is VCC. At 90 degree V0 is VCC, VC1 is 0. Okay, let us write V0, VC1 and 5 angle. 0 degree V0 is 0, VC1, VCC. At 90 degree VC1, V0 is VCC, VC1 is 0. At 180 degree V0 is 0, VC1 is VCC. At 270 degree V0 is minus VCC, VC1 is nothing but 2 VCC, right? So it goes up to 2 VCC. And again at 180 degree it is same as 0, right? This is how we can plot just VC1 waveform here. Okay, with that I will stop here. Next class we will look into the other waveforms such as IC1 and instantaneous power dissipation waveforms. Okay, let's stop here at this point, and if any questions are there I would like to take it offline.